Okay, well, thanks everybody for signing on. Appreciate you being here today for our monthly seminar series for the RAIN project. And our speaker today is Cole Diggins. So Cole recently completed his master's degree here at OSU and is now starting in his PhD program. And he's going to talk to us today about his work with the CRONOS monitoring systems. So Cole, I'll turn it over to you.
Yeah, thank you, Dr. Ochsner. And thank you to everybody for allowing me to come and speak today and give me a part of your time. I just wanted to take this time to help to inform what's going on with the CRONOS project, our Cropland Observatory nodes, and just kind of show some of the work that we've done to validate these systems and to make sure that they're going to be able to be used going forward. So to start it off, what's the purpose? Farmers and researchers require accurate real-time field scale information about conditions within the soil plant atmosphere continuum. They can use this information to make better crop management decisions, predict their crop yields. This data can be used to evaluate and improve crop growth models, or to also use it to develop remote sensing algorithms specifically for cropland. However, most permanent soil moisture monitoring networks don't include active cropland. A lot of the time, they're going to be in a grassland format or something else because of the very destructive nature that is crop management. For instance, the Oklahoma Mesonet, all of their land uses are grasslands. They aren't put into active croplands just because of the active management that occurs in those systems. So, as a joint project between Kansas State University and Oklahoma State University, we have developed a small network of these Cropland Observatory nodes. These portable stations allow us to monitor the field scale soil moisture, which that I'll go into it a little bit deeper here later, but that is located inside of our large box here. It's called a cosmic ray neutron detector. And then we look at our green canopy cover using our trail cam here, and we monitor our atmospheric conditions using our all-in-one weather stations. And as you can see, we're able to just set these up right in the middle of the field and take non-destructive measurements while we're there. So the objective of this particular study was to evaluate the performance of Chrono Stations on working farms during the 2020-2021 winter wheat growing season at these three sites in Oklahoma, USA, or at three sites in Oklahoma, USA. So the three sites that we conducted our study on were at Chickasha, Chattanooga, and Bremen, Oklahoma, across the state, right in the middle of where we would have good wheat production. And this is some information about these sites. So our Chickasha site was planted on October 10th. Our Chattanooga site, September 24th, and our Bremen site, October 8th. And this is some more background information that we can come back to if anybody has questions as well. But going forward, how our Chrono Stations work. So it's an array of multiple sensor platforms, if you will, that we use to collect all of our data in the middle of these fields. So the first thing that we're equipped with is a cosmic ray neutron detector, which you can see here. We utilize for these stations a helium-3 based cosmic ray neutron detector. And then our camera is a Barnow trail camera that we use based toward the crop canopy. And our all-in-one weather station, our ClimateView 50, is up here. This also known as an Atmos 41. We use it to collect a multitude of atmospheric variables. And then, so the neutron detector is this long thing behind the data logger. And then our data logger is provided by Questa, and we use it to collect the cosmic ray neutron data and the Atmos 41 data to send it to our server in near real time every hour, or we shoot for every hour anyway. And the camera here has its own internal cell modem, sending us pictures every couple of hours between 900 and 1700. So to break down all of the different sensors, the cosmic ray neutron detector is probably the one that needs the most explanation, I think, for a lot of the time. So what is so first off, let's kind of break down into what are cosmic ray neutrons. Cosmic rays impact the atmosphere at near light speed and create these fast cosmic ray neutrons, and they're traveling at high speeds. Fast neutrons are slowed by impacts with hydrogen atoms, kind of like what our diagram shows here. So these impacts that the fast neutrons have, it slows them down and does what's called thermalizing the neutrons over the number of impacts that they have. In the environment, over land, soil water is the largest hydrogen pool, because water in general is our largest source of environmental hydrogen. As far as that's concerned, what you're going to find that this could impact is going to be hydrogen. And the best place to find those hydrogen atoms is in water, and over land is in soil water. So our fast cosmic ray neutrons are what we are detecting. So we are detecting the cosmic ray neutrons that have not impacted water, or in that particular case, hydrogen. And so that's all that we're detecting are the fast ones. So our counts end up being inverse to the actual number, or into the actual volume of water. So our cosmic ray neutron counts are inverse to the amount of water that we are seeing in the soils, is the big takeaway. And we can use that data for non-contact field scale soil moisture measurements. And to get to those measurements, there's a few calculations we have to go through. I'd like to break it down really quickly here. So we use our cosmic ray neutron probe, which is the little cylindrical piece I was talking about earlier. We use it to get our raw neutron counts. And then we use the barometric pressure we are detecting at our weather station to get our atmospheric pressure correction factor, which each of these have formulas associated with them. These two formulas you can see down here at the bottom, but these also all have formulas associated with them. But instead of breaking it out for everybody's time, I thought that we could kind of just talk about where these factors come from. The temperature and relative humidity goes into our absolute humidity correction factor. And this NMDB stands for the International Neutron Monitoring Database. So this is an international database of neutron monitors which detects the incoming amount of amount of cosmic ray neutrons, and then we correct and then this is our neutron intensity correction factor. So then we can take all of these counts, or all these correction factors, and our raw counts, and we can use this equation to develop our corrected neutron counts. And then we can put these corrected neutron counts into our calculation of theta. But in that calculation, we have three other variables that we need to consider. We need to consider the lattice water, which the lattice water is the water that is bound up within the mineralogy of the soil itself. So that's going to be a source of hydrogen we need to account for, which we do here in this part of the equation. The bulk density of the soil, just because of the amount of material that we're intersecting with, is something that we have to consider. So we include the bulk density is included in these equations. And then this N0 factor is our calibration factor. So whenever we calibrate for these stations, outlined using Coley et al. 2015 and Desilets and some of the other works that have been determined, we have a calibration procedure I'll go over later, but we are able to determine the volumetric water content that this station would be detecting. And so to calibrate, we actually figure out what the volumetric water content is, the theta, at that particular point, and then we calculate backwards, putting in all of our other variables to get our N0, which then will be the N0 for that station in that field. So and that's where our calibration factor comes in. So now that everybody's been scared of the math and tuned out on me, I'll try to get you back in here with some pictures. So we have our camera, which is a downward facing trail camera, which we use to analyze the green canopy cover. And I kind of talked about when those photos are taken, and it has its own internal cellular modem. So this is essentially how the camera works, is that it is sending us pictures that we then are processing using the Canopy algorithm developed by Dr. Ochsner and Dr. Patrick Nani. at K-State, and we're using that Canopy algorithm to determine our overall green canopy cover. For instance, this picture had a green canopy of 41%. And then for the third part of the soil plant atmosphere continuum is our all-in-one weather station, which is the ClimateView 50 or the Atmos 41. And it allows us to measure precip, air temperature, relative humidity, solar radiation, barometric pressure, wind speed, and wind direction. So it allows us to really look at a lot of the atmospheric variables that are going to be present in this particular system. So moving into that calibration and validation sampling I talked about. So when doing our validation, we collected the soil volumetric water content the same way that we would have done during the calibration, but then during the validation looked at what our cosmic ray neutron probe and our Chrono Station was estimating the theta to be, and then compared that with the theta during our validation. So the way that those samples are collected, we once a month went out and collected 14 validation samples arranged somewhat in a pattern like this, where 6 of our samples came from within 5 meters of the station, 4 of our samples came within 50 meters of the station, and 4 of our samples came within 100 meters of the station relatively. And then these 6 so the samples were then taken and divided into 0 to 5, 5 to 10, and 10 to 40 centimeters and were in depth. And then the volumetric water content of those subsamples was analyzed and used to calculate our soil volumetric water content based on some work done in some of the earlier papers like I discussed. Then, as a second part of our validation, we wanted to be able to validate the excuse me. We wanted to be able to validate the atmospheric sensor against the Oklahoma Mesonet. So in order to do this, we compared it with the nearest Mesonets in Oklahoma. The Chickasha site was 0.14 kilometers away, and the Chattanooga and Bremen sites were 17.6 and 17.3 respectively, away from our Chrono Stations. And then a third part of our validation was also conducted more to look at some of the viability of the systems, make sure that there weren't any crippling errors that we saw, things of that nature. So just to look at the amount of data that was collected in error. So our neutron counts, anything below 500 or 100 counts per hour, raw neutron counts, was considered to be an invalid collection. And then for green canopy cover, we actually broke this out into two. There's 2 kind of classifications that were in green canopy cover. Sometimes we just would not receive an image. And then other times images had issues in the scene during image collection, anything from snow to sometimes the camera would use an infrared filter for no real reason at all. It was just something that we click on sometimes. So that accounts for some errors that we saw in the green canopy cover measurements. And then weather data are actually flagged as issues by the firmware in the Atmos 41s and ClimateView 50s already. So so now we get to really talk about the data. So what we're looking at here in the blue is plots of the Chronos, or is an hourly data set of the Chronos stations. This is the cosmic ray neutron detector after we have corrected for the counts. This is what Chronos is measuring to be the soil moisture after all of our calculations. So we're seeing, so in these blue dots, I just realized I was on the wrong screen to be using my pointer. My bad, guys. But so we can use these blue dots and we can see our soil moisture. The red lines here, the red bar graphs are precipitation events. These red diamonds are our validation samples, collected in the same way as the calibration sampling like we had talked about. This is the soil moisture that we observed as a ground truth through our soil moisture sampling. These magenta lines are what the Oklahoma Mesonet was predicting soil moisture to be. So this is what the Oklahoma Mesonet was detecting this as the soil moisture. So these are the nearest Mesonet sites. And the black dotted line that we see here is the wilting point. So this is the wilting point for each of these particular fields, the permanent wilting point, I should say. So 3 things I'd really like to point out is that we had good agreement between our CRONOS stations, the soil moisture they were detecting, and the ground truth validation soil moisture measurements that we took. We had really good agreement there, as you can see. We did not have a good agreement between the Oklahoma Mesonet and the Chrono Stations, or the validation for that matter. So we didn't really see a good connection here between the Oklahoma Mesonet and our CRONOS soil moisture data. And that could be for a number of reasons. We're not really sure exactly why, but it comes into play that we had great connection with the site at Bremen, where the Oklahoma Mesonet actually lined up very well with what we were predicting to be the soil moisture. So it's something where we had 2 sites that were not very useful, and then we had the one site that was very well correlated with what we were seeing. And then third that I'd like to point out is the permanent wilting point right here in April. So if you see that, we actually our soil moisture dipped down below the permanent wilting point at this point in April. And I really want to put that into your mind real quick, because I want to come back to it here in a moment as we look at our green canopy cover. But first, I'd just like to show this is the soil moisture from our CRONOS validation sampling when compared with our CRONOS soil moisture estimates that we were taking. As you can see, we had really good correlation in NSE of 0.75 or 0.76. And all in all, we had good connection between the 2. As we move into the green canopy cover, we saw a little bit more variability in these particular readings. So not only did we see variability across the field, as seen by the standard deviations of our validation points. So real quick, just to be clear, at each of those 14 spots that we talked about with the soil moisture, these were these red diamonds represent the average green canopy of pictures taken before sampling at those sites. So we took a green canopy cover picture, and that is where the average comes from for this data. And then, as you can see, even throughout the field, we saw some pretty wide variability in the green canopy cover measurements at the Chickasha site, but had overall decent agreement at these 2 sites. However, at the Bremen site, we had a large underestimation of the green canopy cover, largely just because, you know, we have such a small scale. We're looking at a very small area when we're taking these when compared to the size of the field. This isn't like our soil moisture where we're getting a large area incorporated into that amount. This is simply just a small picture. So that is something where we see this as an issue. But I want to bring you back to this point here in April. So where we see that after that large drought that occurred across Oklahoma, we still see that the crops were able to continue to thrive at our Chickasha and our Bremen sites for another month or so. They were able to still grow and continue growth. But at our Chattanooga site, we continue at April, we essentially just continue on to senescence, and our crop ends up terminating. I want to bring you back to this soil moisture point where around the same time, we end up going below the permanent wilting point. And we're able to see and understand, thanks to the wide-reaching vision of these stations, of the soil plant atmosphere continuum, we're able to really see that effect and understand it better as we see that green canopy cover drop, knowing the soil moisture had dropped that low. Now the camera, there is really no way to sugarcoat it. We had some legitimate issues regarding the cameras. They aren't really, in regards to the field average, they are not really in their current state able to effectively determine the field scale green canopy cover. They might be able to determine it for that particular spot that we have them in, but as a whole, they don't necessarily represent the field entirely. So that's something that we saw. And then moving on to the atmospheric sensor, this is a plot of the daily maximum and minimum temperatures measured by our weather station. So that would be an hourly average temperature measured by our weather station. And those are the dots, and then the lines are the temperatures measured by the Oklahoma Mesonet. So these are the maximum and minimum temperatures saw by the Oklahoma Mesonet, max and min over the day, and that is the line, and then the dots are our Chrono Stations. And as you can see, we had almost an exact correlation between the two, and very accurately we're determining our temperature. And just to break that out a little bit further, first we can look at our precipitation. Now, the precipitation had overall a decent correlation, but we were underestimating our precipitation. When compared with the nearest Mesonet site, our precipitation was being underestimated at the CRONOS sites. Now, this could be for a number of things. Likely it's due just to the small catchment size of the rain gauge. It's just a small capture size, and when you couple that with these Oklahoma winds, you're going to lose some of that sample. So that's why we are seeing some of this underestimation. Our temperature, min and max, we had great correlation between those, and overall they did really well. And these were even able to perform during extended periods of winter storm. They were still really performing well, and we were still seeing good results when comparing that with the Oklahoma Mesonet. Now, our solar flux density, our solar radiation, we had good correlation, but we were underestimating it. And this last week, actually, I talked with some of the folks from Meter Group, and we were able to come to a bit of a realization where we didn't realize that there was, or at least I didn't, that there was a correction factor that needs to be applied when using the bird spikes on those particular systems of about 5%. And so that would at least account for some of our underestimation, where we need to raise that value up based on those parameters. And then also the rest of it, those pyronometers can get a little dirty, so you have to clean them off quite a bit. And I think that that's also where we might see some of that underestimation coming from as well. Moving on, our barometric pressure was very well correlated with not a lot of deviation from the actual values, and which is great, especially when you consider it's one of the main factors that goes into our calculations. And then our wind speeds were really overestimated by our stations. I'm not exactly sure why that is, but our stations were at the 2 meter, when compared with the 2 meter distance at the Oklahoma Mesonet, were really overestimated using these systems. But yeah, and then to look at our reliability, this is our reliability chart. So you're looking at the error that each of the systems on the Chrono Stations had. And essentially all of the others were 2% or less in their overall error rates. Data came in really well. The sensors that were represented here had very few errors, which is great. And then we get to the camera, which about 18% of the time did not actually send us a image. It just never sent one. And then the remainder of these errors come from images in the scene, such as maybe a camera, moved off of its mount, or just snow, which all of these error images were also excluded from overall calculations. But there were a lot of issues in the scene, and I and one of our students went through and looked at all of these images to determine how many of them were in error. So there were quite a few that we had that were also an issue. And then, and so just to conclude, we were able to, I didn't say that. And just to conclude, we were able to effectively measure our soil moisture and estimate it well with the Chrono Stations. Our spatial variability was a clear issue for the cameras and led them to have issues with estimating the overall field average canopy cover. And our air temperature, solar radiation, atmospheric pressure were all closely related to the Oklahoma Mesonet. And as well, they all worked relatively well, that weather station did. Now, next steps for our project, we are looking at developing a new camera using some Raspberry Pi technology. That's being done by I don't know if he's considered a former REU student still, but he was our REU student this summer and he's continued to work with us. Connor Colby, he's been developing some of those cameras. And then also we're looking to, a new prototype we're working on is using one moderated and one unmoderated cosmic ray neutron detector to look at crop biomass and see if we can use that to estimate the crop biomass of the field. I'd just like to give some acknowledgments real quick. I'd like to say thank you to the RAIN project, not only for your time today, but also for funding this grant and allowing us to conduct this research. I'd like to say thank you to our farmer cooperators with whom this active research would not be possible. And I can't thank them enough. A thank you to Dr. Arnault and Michael Pettyjohn for their help at the Chickasha site. And I'd like to also say a thank you to Jerry Brown and Samantha Burns, which are a fellow grad student and an undergraduate student here. And then our two REU students we've had over the years with Maddie Morris and Connor Colby for their work that they've done on the CRONOS project. And with that, I'd like to say thank you all for your time. And do you have any questions?